In example 3, we need to solve each equation for the variable indicated, and if necessary, round to the nearest thousandth. One thing that you should do is you should take a look at the position here in the parentheses or the argument position, and note that it has to be greater than 0. So we have to place some restrictions, or at least watch out for some values. We know that r minus 9 has to be greater than 0, and also r minus 5 has to be greater than 0. So we could add 9 to each side. R is greater than 9, or add 5. R has to be greater than 5. This is the more restrictive one over here on the left, so we really don't even need this one. We can just take a look and make sure that R is greater than 9 when we're all done solving this. If we look at the original problem, we've got a log base 5 on the left and a log base 5 on the right. There's a few different methods to solve this. I'll show you one method here, and that's just grouping the logarithms with the same basis together. So if we subtracted log base 5 of r minus 5 from each side, it would cancel here, and we'd be left with log base 5 of r minus 9 minus log base 5 of r minus 5 is equal to 1. We can now combine these logarithms. They have the same base. Remember that when we're subtracting logs, the rule is that we write the left position divided by the right's position. That's equal to 1. What we can do now is change this into an exponential. So this is 5 to the first power is equal to r minus 9 over r minus 5. If we multiply each side by r minus 5, remember to do that in parentheses, this will cancel. We'll be left with 5 times r minus 5 times 5, which is 25, is equal to r minus 9. If we solve here, we can subtract r and add 25. Getting a little off the screen, we'll move that up. And 4r would then be equal to 16. We can divide by 4, and r will be 4. Keep in mind though, our restriction, r has to be greater than 9. So actually, this is not a possible solution. Here's why. If we took r to be 4 and we substituted into our equation, we'd get 4 minus 9 here, which is negative 5. No power of 5, positive or negative, will get you a negative number. If we take 5 and raise it to the negative 100 power, it's just a little bigger than 1, but very close, or excuse me, 0. It's just very close to 0 though. Because that 5 to the negative 100, you just move 5 to the 100 down into the bottom, and you'd have 1 over a really big number, which is just really close to 0, but it's non-negative. So this position here cannot be negative. With that being the case, this is not even a possible answer, so we have to conclude that there is no solution. No value for r will actually make these two sides equal. We're going to take a look at the one on the right hand side now, and this one, instead of having two logs, we just have a number here on the left and a number here on the right. So in this case, I think it's going to work out best if we just get the logarithm on its own on one side. We need to get rid of this 4 to do that. So this is log base 5 of x minus 1 is equal to 1. And even before we continue, I'm just going to go ahead and take a look at this position, x minus 1, and we know it's got to be greater than 0. So if we add 1 to each side, x has to be greater than 1. If we continue solving this, we've got 5 to the first power is equal to x minus 1 if I change this logarithmic equation into an exponential. Adding 1 to each side, this would be x is equal to 6. 6 is definitely bigger than 1, so we're good to go. 6 minus 1 here is 5. 5 to the first power is 5, so log base 5 of 5 is 1, and 4 plus 1 is 5. So you can check it in your head with those easy ones, and if not, just take that value, substitute it in, and then go ahead and use your calculator to see if you've got the right value. But 6 is definitely a good one for this.